Today we're diving into Chapter 5, which covers the core logic underlying all statistical tests. When we collect sample data, we often observe differences between groups, such as varying average depression scores between men and women. However, before drawing major conclusions, we must ask a critical question. Is this observed difference a true reflection of a population pattern, or simply an artifact of random sampling chance? This chapter establishes the fundamental conceptual framework that researchers use to answer that question, setting the stage for inferential statistics throughout social science research. Whenever researchers analyze sample data, they must evaluate two competing explanations for their results. The first explanation is systematic variation, which means that the effect or difference you observe in your sample is genuine and reflects a true relationship in the broader population. The second explanation is random variation, also known as sampling noise, which occurs because no two random samples are identical. The primary job of any statistical test is to evaluate which explanation is more plausible by comparing the magnitude of systematic variation against background random variation. Point estimates provide a single sample statistic as our best single guess for a population parameter, such as estimating a population mean depression score at 1.80. However, point estimates alone do not convey uncertainty. That is why researchers construct interval estimates, most commonly confidence intervals, which establish a range of plausible values around that point estimate. When comparing two groups, if the confidence interval for the mean difference includes 0, we cannot rule out 0 as a plausible value, meaning there may be no true difference. If the interval excludes 0, we have stronger evidence of a real population difference. Statistical power is defined as the probability that a study will correctly detect a real effect or population difference when one actually exists. A low-power study risks missing genuine relationships, leading to false negatives. The single most significant determinant of statistical power is sample size. Think of sample size as camera resolution when trying to read a blurry license plate. With a small sample, random noise obscures the letters. Increasing the sample size enhances image clarity, making it far easier to isolate the true underlying signal from background sampling noise and accurately detect subtle relationships. Sample size dramatically alters our statistical sensitivity. Imagine examining depression scores. In a sample of 20 students, a real population difference might easily be hidden by random sampling variation. But with 2,000 students, that exact same difference becomes easily detectable because standard errors shrink. However, massive sample sizes introduce a secondary challenge. They can yield statistical significance for differences so tiny that they hold zero practical importance in real life. Therefore, smart researchers never rely on statistical significance alone. They must always examine effect size to determine whether a statistically significant finding is practically meaningful. Statistical inference allows us to make confident statements about entire populations based on sample data. But these conclusions depend heavily on three core assumptions. First, the sample must be representative of the target population. Biased sampling invalidates statistical findings regardless of sample size. Second, the sample size must be large enough to minimize random variability and afford adequate statistical power. Third, the chosen statistical procedure must properly align with the data scale and research design. Fortunately, many modern inferential methods are robust, meaning minor violations do not completely invalidate results, though major violations severely impair trustworthiness. This chart illustrates the direct relationship between sample size and statistical power. As sample size expands from small to medium and large, the study's ability to detect true population differences increases substantially. In small samples, statistical power is often low, frequently below 30% for small effect sizes, making it difficult to distinguish true effects from chance. Medium samples offer moderate power, while large samples push power above 90%. Higher statistical power ensures that research studies are adequately equipped to discover real phenomena, preventing valuable research questions from being prematurely discarded due to insufficient sample sizes. Chapter 5 covers several vital learning objectives that form the backbone of quantitative research literacy. First, you can articulate why formal statistical tests are necessary rather than simply comparing raw sample averages. Second, you can clearly differentiate systematic variation from random sampling noise. Third, you understand how point estimates and confidence interval estimates work together to express estimate precision. Fourth, you recognize how sample size directly controls statistical power. Finally, you can identify the three key assumptions underlying valid statistical inference, enabling you to critically evaluate research findings throughout your social science coursework. Throughout this course, our overarching empirical investigation centers on understanding why certain college students experience higher levels of depression than others. Now that we understand the logic of statistical testing, we are equipped to evaluate specific research hypotheses. For instance, we will test whether observed depression differences between men and women reflect true population disparities or random chance. We will also investigate relationships involving stress levels, self-esteem, and generational status. The logical principles established in this chapter provide the exact decision-making framework we will apply when analyzing real student survey data in upcoming chapters. As we conclude Chapter 5, we transition from theoretical concepts to practical application. The fundamental logic we discussed today, weighing systematic variation against random sampling variation, applies to every statistical test in the social sciences. In Chapter 6, we put this logic into practice using our first formal inferential tool, the independent samples t-test. Rather than introducing a completely new philosophy, the t-test simply operationalizes Chapter 5's principles, providing a mathematical formula to test whether two group means differ significantly. Armed with this conceptual foundation, you are fully prepared to execute and interpret inferential statistical tests.